And finally, let's find the residue of this function at infinity. And here let me remind you that the residue at infinity of the function is defined as the negative c negative 1, the coefficient of Laurent expansion at z tending to infinity. And as you remember, there is always a question in which direction to infinity to go. Of course, you should always try to find the most suitable direction. So how to choose it? Well, that's a method of trial and error. For example, let's try horizontal direction. So we draw some point at plus infinity and connect our reference point with this infinitely distant point to the right. And let's trace the changes of the argument of our constituents. For example, the change of the argument of number z minus I. We see that it rotates in the counterclockwise direction by angle pi by 2, but not quite, because it's almost pi by 2, but still there is a small angle, and from trigonometry you can find that its tangent is 1 over x. So in fact, the real change of the argument of this z minus I number is pi by 2 minus arctangent of 1 over x. And the same goes for the second number, z plus I. It's negative pi by 2 plus the same kind of arctangent. And unfortunately, you will have to expand all this expression, including these changes of the arguments, in 1 over x. So you will have to deal with the expansions of arctangent, which is doable, but not that suitable. So there are other directions in this problem which will allow you to avoid that kind of unsuitable arctangent expansions. For example, let's try a vertical direction, like upward or downward direction. Let's try upward direction. And you immediately see why it's simpler, because now the delta argument of z minus I is exactly pi in the counterclockwise direction, while the change of the argument of z plus I is strictly 0. And that's why it's more suitable. And this is how we proceed. We parameterize our complex number as iy, where y tending to plus infinity, and write down the expression for our multivalued function. So f of iy equals iy plus I divided by I modulus to the power of 1 minus gamma plus iy minus I divided by minus I to the power of 1 plus gamma, and times the corresponding change of the argument of our function. So we have to multiply our change of the argument of z minus I number, which is pi, to the corresponding power, which is 1 plus gamma. And multiply, of course, by f of plus 0, which is 1. And now we simplify our moduli. So we obtain y plus 1 to the power of 1 minus gamma and y minus 1 to the power of 1 plus gamma times e to I pi plus I pi gamma. And now we can analyze this expression using purely real analysis arguments. We simply expand these two real brackets using Taylor expansions. So we factor out y, end up with y squared times 1 plus 1 over y to the power of 1 minus gamma times 1 minus 1 over y to the power of 1 plus gamma. E to I pi is turned into negative 1 and e to I pi gamma. As you remember, we are hunting for 1 over z term, and that means 1 over y term. And that means that we'll have to expand both these brackets with the accuracy of 1 over y cubed. It's a simple binomial expansion, but I'm a little bit lazy to do it with bare hands, so I'll use Wolfram Mathematica. So let's do this. So we write down series coefficient of 1 minus 1 over y to the power of 1 plus gamma times 1 plus 1 over I to the power of 1 minus gamma. And we need to find the expansion at infinity, and the order is 3. And here we go. And alright, here is our expansion coefficient. So we'll write it down as dots plus 4/3 times gamma times 1 minus gamma squared and times e to the power of I pi gamma with negative sign. And of course we need to add here 1 over y and plus dots. Next we should switch to our z notation. So y is equal to z over I. And we obtain our c negative 1 coefficient, which is simply minus 4/3 I gamma times 1 minus gamma squared times e to I pi gamma. So our residue now is simply 4/3 I gamma 1 minus gamma squared times e to I pi gamma. And this basically completes our discussion of power type multivalued functions. So I hope you find it instructive and enjoyable, and you'll use it extensively in your future work. Good luck!